Okay, we're trying to solve this ceiling exponent equation. Solve. Find values of x that satisfy this. Now, just an idea of what this 2 to the x looks like. 2 raised to the ceiling of x. The ceiling of x is the least integer greater than the input argument. It's the opposite of the floor function. Now I'm just going to sketch this. First of all, I want to say that it inherits this property from just 2 to the x. This is kind of the discretized version of 2 to the x, which is always positive. There's a finite or countably finite number of discontinuities on this thing, which really isn't important as far as this problem goes. But just a rough idea of what we're looking at right here. Let's say that this, we'll just label this the x and y axis right here. Now, the ceiling of any number between 0 and 1 is just 1, okay? So we would count up 2 units because 2 to the first, it would have a constant value of 2 raised to the first power. So in other words, this is 2 to the 1. And again, folks, that is because the ceiling of any number between 0 and 1, including 1, is 1. Now let's jump out to 2. Okay, and then this, I guess what they call it, jump discontinuity here. But then we are literally gonna jump all the way up to try to make this marginally scaled. Okay, so right here, this is 2 squared. Okay, and then so on. So you can see it grows like the exponential function in sort of a discrete way. And the behavior to the left of the x-axis, it's always less than 1. And that's not hard to verify, but it's always positive. Okay? So, and this is important right here. 2 to the ceiling of x. And you guys can verify. I don't want to waste too much time. It's fairly straightforward to verify that this is less than or equal to 1. Whenever, because you just have powers of 1, 2 to the first, 2 to the 0, which is 1, 2 to the minus 1, which is 1/2, 2 to the minus 2, and so on. So they're still going to be positive small numbers. So this is true whenever x is less than or equal to 0, right? So this property follows very quickly just from the fact that 2 to the x is positive, I guess. All right, and so these two statements, we'll just leave them to be truthful. Now what that does, it helps us a lot. Like if we have a solution, that means that any solution, I'll call it S, has to be strictly trapped between, I don't know if it's strict necessarily, 43 over 7. I think it is strict, probably. All right, so like this. And what I'm trying to convey here is any solution to this equation, I'm calling it S, this is our search interval, and that's what this is implied by these two statements, okay? So we've cut down our search by quite a bit here, actually. So this is a number, a little bit more than 6. So this motivates the following process here. We're just going to check all these intervals all the way out to about here, and just see what happens. Now, again, folks, just as I won't write them all in here, but the ceiling of x, I'm just using this as an example. I'm not going to write them all in. But the ceiling of x right here is equal to 3. Right? Again, it's the opposite of the floor function. That's exactly where this 3 came from. Right? This 3 and this 3, you were just substituting in right here. Okay, so that's what's going on there. And again, I won't bore you with all the arithmetic, but I got x equals 41 over 7 right here. I guess I lost my marker again. Okay, right here we have x equals to 41 over 7. Okay. Now, y'all notice this is not a solution because 41 over 7 is not in this interval. Okay, so this is, I'm writing this down, but this is, how do we say that? This is not a solution. Okay, and then, so also you would get x equals to 39 over 7 on the next one. So 39 over 7 is not in this interval. 39 over 7 is a number bigger than 5, right? Now, they start to go down quicker here because of the exponential growth here. 2 to the first, 2 squared, 2 cubed is 8, right? So what I got right here was x equals to 35 over 7. Yeah, 35 over 7 right here. Now again, we do have to check. This is what it would be. That would be the solution to this. But we do have to check to see if it's in the interval. And 35 over 7 is a number. Oh, that's just 5, isn't it? 35 over 7 is just 5. And 5 is not in this interval, right? But now notice 2 to the 4th is 16. And so it's going down quicker. And so what we'll end up with is x is equal to 27 over 7. And, I'm pretty sure I got the arithmetic correct. All right. And it turns out this is a number between 3 and 4. It's just underneath 4, right? In fact, it's 3 and what? 6/7? 3 and 6/7. So this one would be a solution so far. Okay, that's one solution. We don't know how many there are really. There could be more than one. There's nothing about the equation that would make you think there'd only be one. Now, when you do the work on this, though, let's see, I got x is equal to 11 over 7. You see it's going down. This is 32, right? So it's jacking the answers down pretty fast. So you have x is equal to 11 over 7, right? Which clearly is not in this interval, right? So this was our only survivor. And we don't have to go any further than this based on just the search domain. You can tell it's going to be negative on the next one, and that's not going to work because the too elevated to the ceiling of x is always a positive number, all right? So 27 over 7 is the only solution that I got on this thing, folks. And I'm pretty sure it's right, but again, I've been wrong many times. But I just like this solution process. There's a way to do this with logarithms too that's perhaps a little, I don't know if it's any faster, but you can actually take the log of this and bring the floor function out to the front. Log base 2, in fact, is the way to do it. So, but anyway, we got 27 over 7 as the solution. Let me come up here and write that in here.